All right, let's start. This is Dr. Yuzo, ECE 341 Power System class. And today is our 12th lecture. Can you guys hear me? And also being able to watch my screen, share the Gantt chart. All right, thank you too. Thank you, Amy. Let's move forward. So today we are here. Okay, the very first cell here, because I moved the freezing the first column and moved the Gantt chart a little bit. So week 7, believe it or not, is already week 7. Monday today, and first lecture for our new module 4, power flow studies. Okay. This is where we at, and also be noticed that by the end of this module, we will have a project assigned, which will be due in a month from there. Okay. So as you can imagine, the project is about this module 4, the power flow calculations. Okay. Requires the use of MATLAB. Have you guys received my notice about the good news about our MATLAB? Good, good. Are you guys kind of hooray? You should. You really should. We appreciate IT as well as the school for this. But anyways, let's come back to our knowledge module 4, power flow study. What this module is about? What this module is about is simply about the study, or say trying to find, basically. Find means what? Just calculate. So this module is all about the calculation. So you're going to use your calculator quite often, because operation is always among bunch of phasors and complex numbers. Calculate what? The power in a interconnected network. Using a per phase network in per unit. Again, this is we're going to see a per phase network. A perfect network means what? Once again, I explained this in the very first lecture of the semester. Okay. The real system, of course, this is a power bus, one power bus, 3 phase. So we have 3 lines or 3 cables, right? You have another different level voltage power bus. Again, 3 phase, 3 lines there. The connection is like this, right? Your phase A to phase A, and phase B to phase B, phase C to phase C, right? Stuff like this. Right? However, what does it mean by per phase? Perfect network is we just choose one, and then one connection in between. And then call this bus 1. This is bus 2, right? Without presenting all of the 3 phases cables, we just are using one cable, right? One cable, one phase, right? And in between, of course, therefore also one connection. So this is so-called per phase network. And what does it mean by in per unit? Per unit means a given voltage and power are in what? Per unit. So what you're expecting to see is maybe B base is provided, or say the power base is also provided for you to be able to find the real value, the actual values. Right? Does it make sense? So these are two things you need to understand. Okay. Power system connection might be very complicated, okay, even though we won't study very complicated ones, but it could be very complicated. However, we are using but just a per phase network. Okay. So one bus is represented by one single bar here, and the connection between two buses is just one line connection, and everything is given in per unit. Therefore, you probably need to be very careful on the base value. This is the what this module is about. What this module is about. And the first thing we learn from this module is not the power yet, but some iterative solution of nonlinear equation. It's a math, it's a mathematics, as the first thing we're learning. Why we are learning the math? First of all, the power equations. The power equations are nonlinear equation. What is mean by nonlinear equation? Anyone knows what is mean by nonlinear equation? How you tell that this equation is nonlinear equation? It's not difficult, right? It's not something difficult. Let me give you an example. And looking for what? The roots, the x. Is this a nonlinear? Yeah, parabolic. Quadratic. Yes. Quadratic equation. Power greater than 1 on variable. Yes, good. You guys understand this. Okay, this is very good. Okay, very good. I think a basic algebra concept. You're good. And for example, this is a typical nonlinear equation. Nonlinear equation. Next is the dimensional. What does it mean by n-dimensional? Or say n-dimensional nonlinear equations? What does it look like? Or say n-dimensional? Anyone can tell what does it mean by n-dimensional? 1D, 2D, 3D, 4D, etc., right? This is dimensional. But in terms of the equation, then what does it look like? How can I tell this is an n-dimensional nonlinear equation? How can you tell this? Anyone knows? Or any guessing?
There's multiple potential solutions, not just one, to the equation above.
It's close, and the Sawyer's answer is also close. The one dimension, which means what? You have one unknown, one variable x, right? Then how can you tell the system is n-dimensional? You have up to what? N unknowns, right? Up to n unknown variables. However, what you see is what? number of equations, first of all. And the second is number of unknowns. Does it make sense? Number of unknowns is n-dimensional. However, to be able to find all of them, what do you need to do? Same number of equations. So what does it mean? N-dimensional nonlinear system, what do you see? Simultaneous equations, right? N. You have up to n simultaneous equations. N-dimensional. The first of all is the number of equations. You're seeing n up to n equations there. So this is dimensional. Dimensional. So this is why, obviously, one dimensional. It's one dimensional. Only x is unknown there. Yeah. This is a little bit concept. Not difficult, but with that being said, let's learn the so-called iterative solution, or say iterative mathematical method to solve the nonlinear equation. Okay. By the way, you guys probably learned some already from the 302, right? If that is the case, that would be great, and that would be great. The first method we will learn is so-called Gauss method. Actually, Gauss-Seidel method. We're going to learn two methods. The first one is Gauss method. Second is Newton method. The first Gauss method. Have you guys learned this before? Probably you do, but have you? Anyone? Good. Very good. Very good. If you have done that before, then I think this is gonna become easier to you guys. So what do you have? So a nonlinear equation which is defined as f of x equals to 0, which makes perfect sense. Is one dimensional. Okay, let's just study the one dimensional. Right. Just a one dimensional. Okay. We don't need to worry about the n dimensional. It was easier one. So one dimensional nonlinear equation f of x equals to 0. And what you want to do is to find root x, right? So the description of the problem. Now how you do it? Procedure. Let's briefly talk about. So the procedure is like what? First, we'll derive x, right? This is the equation itself. Without doing anything, if you directly derive x, what you can end up with is another function which is different from f. So we call it g of x as well. You're not solving it. So this result is not the solution. Okay, it's obviously not the solution. Your x is in terms of x. No, it's not solution yet. But this is our first step. The first step, based on which we need to do what? Initial value x of 0. In this particular class, it's not math 341, so the initial value is given. The initial value is given. Because trust me, the initial value, if it is not given, is quite a big trouble. Since you have learned this before, you know that different initial value might lead you to the correct answer or completely messed up. This initial value absolutely matters. Absolutely matters. Okay. So luckily, in this course, it is given. With this given initial value, what we want to do is start to derive the first step iterative result of x equals to what? Just substitute the initial value into the g of x on the right-hand side of the equation here. So after you receive this first order, the first step iterative value for x, what do you want to do next? Check, right? Check what? Check the magnitude of the difference between two steps, x result, to see if it is greater or less than epsilon. And what is the epsilon? Anyone remember what we call it? Accuracy. It's called accuracy. The smaller, the higher what? Resolution of the root. Does it make sense? The smaller accuracy you choose, and the higher resolution you can receive from your root, from your solution, from your solution. It's called accuracy. And obviously, you have two scenarios. If this magnitude less or equal than epsilon, or the otherwise, right? So if it is equal or less than epsilon, what does it mean? What do we say? Anyone remember? Anyone remember? We say hooray, right? What does that mean? We're done. And who is the solution? The initial value is the solution, or say the root. Of course, it's almost impossible, right? The first step you turn out to be initial value is the root. Well, if we can do this, well, we'd better to go to buy some lotteries. And 9 out of 10, or basically even 10 out of 10 cases, is not true. It's not true yet. So the difference between the first step and the initial value is greater than epsilon. Not done. Not done yet. We know what initial value is not the root yet. But what do we do next? What do we do next? Anyone remember? Go for the second step iteration, right? How to derive the second step iteration? Easy. Same as the first step. Substitute what? The first step iteration result into the g of x. You got x of 2. Second iteration result. Does it make sense? And after you have the x of 2, what do you do? What do you do? Check again, right? This time you're checking what? Checking the difference between x of 2 and x1. Let's give the question mark. Right? From 302, basically, I think is about same thing. Should be same. And here you obviously gonna have another 2 scenario. One is if these checking turn out to be true, what do we do? What do we do here? And of course, if not, what do we do? First, if the difference between these two is small enough, say equal or less than epsilon, and then what do we do here? It's a root, or say what we should say, hooray, right? Once again, hooray. And what do we say? Who is the root? X of 1. X1 is the root. X1 is root. This is like the first checking you are able to tell if or say whether x of 0 is root. And then after second checking, you are able to tell whether x of 1 is the root, right? And so on and so forth. And this time, 9 out of 10, you are not going to have this to be true. So if the difference here, the magnitude of it, of course, the magnitude of it, okay, the magnitude of it is still too big, means what? X of 1 is not root. We got to do what? Go for x of 3 by conducting next step iteration like this. Does it make sense? Derive the next step iteration result, and then to check. Based on the result of a check, you decide to move on or just stop. Okay. And after this, again, check. Right? This time, check whom? Difference between x3 and x2. And so on and so forth. And the rest of the step we can skip. Any questions regarding this procedure? This is same as what you guys learned from 302. It's about same. Come on, speak. It's time to it's the time for you to use your mouse rather than your fingers.
Can we get an example?
Yeah, absolutely. We're gonna definitely go through the example. But how about this procedure? Is it same or making sense?
Yes.
All right, good. Then we follow by example. We will see more details. But before example, I would like to. What's the sense of such kind of iterative method? What's the sense? How to kind of viralize this math, right? I don't know. Have you guys ever think about this question? What did they?
Well,
You're
eventually,
checking.
a
Yep.
solution
Go ahead.
converge. You should get some sort of solution.
Very good. Very good. I like that. I like that. I like that term very much. Converge to a solution. Very well. Okay. How to understand the iterative method is like like this. Okay, let me give you viralized. This is kind of, it's not T. It's a step. Obviously, go along with more steps. What's gonna happen? This is the unknown, the variable X. How it works? You do your iterative method. It's gonna do this. So many of you guys are taking 360, right? What are you seeing here? You have a transient, right? You have a transient, and after some transient, you're reaching what? Steady state, right? This is steady state. This is what? The steady state value. Right? The steady state value. And this thinking over checking is checking to see what? Your previous step result, the difference between previous step result and the current iteration step result. The smaller it is, the steady state it will be, right? The more steady state it will be. Does it make sense? Because look at here. Your previous step is here. Your current step is here to see how big the difference between these two results. However, after some steps, you see how big is the difference between these two steps. Very small, isn't it? And when it completely stabilized onto a constant value, which is steady state value, is also the solution. What do you see? Step here and step here. What's the difference between these two values? 0, basically, right? Does it make sense?
And when you don't have a solution that will converge, then what?
Won't converge?
Yeah.
Well, generally speaking, it means you chose the wrong initial value. If you choose the wrong initial value, it absolutely possibly go like this. In control system, what we call it? Unstable. Okay, so your initial value choice is very, very critical. And that's actually beyond the range of this course. So it's not a math course. So we don't want to go that far. So the initial value we are choosing is guaranteed that it's gonna convert. Maybe we choose from here. Maybe you choose from here. But anyways, it's along this path towards the converge. So it's the stable. It's stable. So if you choose here, well, let me ask, you choose initial value here and the initial value here, what's the difference between this 1 and 2? What's the difference?
The amount of steps you'll have to iterate.
Very good, very good. It's just a different amount of the steps you need to reach that steady state value, right? It's how far away you're from the steady state value. Like you said, if you have enough luck to win the jackpot, your initial value is here, right? It won't happen in the exam, I guarantee you that. But in real life, maybe you have a chance, maybe, which is again almost impossible. Does everything make sense? This is how you understand this math. Okay, it's actually you want to visualize why we are doing so. What's the sense? It is here. It is here. Okay. But by the way, I don't believe any one of us has enough luck to have a jackpot. Okay? So just calm down and focus on our study and thinking of find a good job in future. Okay. All right, let's go through one example. I use Gauss-Seidel method to find the root of pretty much one equation containing one unknown. We have used this same equation as example at the first place. And now let's just really apply this method on this one to find x value. And the nice thing is, first, the initial value is given as 2. Accuracy is also given as, you can imagine, it's definitely a very small value. Definitely a very small value, otherwise it makes no sense. Right? Accuracy required as 0.0001. Okay. Let's see how to find this x. Okay, go over this procedure together. All right, so according to the notes, with this initial value, we need to first of all derive what? X01, right? Oh, of course, before X01, you need to derive x. From this f of x equals 0, derive x. What's the easiest way to find x in this one? Of course, you don't want to derive this x by eventually conducting a third order square root, right? This is that's the cubic roots. Why the h we want to do that, right? So we don't want to do that. We don't want to do this either. We just simply derive this x. How about that? Don't make the things even worse. Okay. So derive this x is the easiest choice. Equals to make sense? And this is nothing, of course, our g of x. G of x. Nothing, just very simple algebra, just to derive this x here. Result is in terms of x, so it's not solved. It's just pretty much reorganize this given equation. And then from here, we go ahead to derive x of 1. The first step, iteration result. So is equals to what? Negative times 2 cubed plus 2 squared plus. Does it make sense? What you're doing is just what? G of x of 0, right? So substitute x by initial value. In the exam, just to make sure you calm down. You calm down to do this algebra little by little. We have definitely multiple iteration steps, but if you make mistake, even minor mistake, what do you see? What could be the consequence? Can you imagine? Never convert, right? You can never convert to a solution. After 100 steps, which cost you 3 hours. You still cannot find the root because of small, minor mistake, maybe in the first iteration. That's absolutely possible. Absolutely possible. So after conducting some math here, you are receiving a result 2.2. Does it make sense?
In the exam, do you mind if we use like our, if we have like graphing calculator, we could do like
And graphing calculator, how would that help you do the iteration steps?
because if we
You can
like,
find it, well, you can find a solution easily. That's true. However, I'm watching your procedure and give very little point to your final result. And then can your calculator do the iteration job for you?
well, like I'm just saying, like if you type in the function, couldn't you just type in start with 2, hit enter, it'll give you a value, and then you'll take that value and then just basically keep iterating, right? Or do you want us to show every single summation in the polynomial?
Well, that part is you're relying the calculation here on the calculator. That's what you say.
Yeah.
That's fine, of course, fine. Showing this, well, this quite a bit the point here, and then your first step maybe you can write here as what? If I gonna attend the exam, I'm gonna do this. And then you give me a result here. You use your calculator to do this algebra. Of course, you're gonna use your calculator. No problem. But your steps, your procedures cannot be helped by a calculator, right? I mean, the calculator is not able to, right? Am I right? Just like the calculator cannot teach you the lecture, right? Let me know if I'm wrong, okay? I'm gonna discuss this with the permanent chair. Sawyer said, I have never heard of anything like that. Well, even if you have, well, I don't mind. If calculator can do something for you, well, not seeing any reason I should stop you from doing that. But the procedure, the middle steps, I doubt it. I doubt it. All right, coming back to this the solution here. Is 2.2 okay here as the result? Very good. Amen. Why is not okay? Come on, guys, speak. It's the mouse work. It's not your fingers work. It's too big. It's too big. And, well, accurately, it's the difference is too big, right? The difference is too big. The difference is too big. And also, another thing is you guys need to be very, very careful. Okay. There's another reason for this 2.2 as result not okay. Now listen carefully. Look at the accuracy. What do you see? 1, 2, 3, 4, 4 digits after the dot, right? What does it mean? Never forget, you're going to compare your difference between two iteration results with this accuracy value. So to do that comparison, you need to guarantee what? The difference also has at least 4 digits, right? That doesn't make sense. To make your difference to have at least 4 digits after dot, your iteration results for each step must do so as well. Does it make sense? So 2.2 is not okay in terms of the number of digits after the dot. So remember this. Okay. 2.2222. Okay. 4 digits. Okay. So you can imagine afterwards you're having the same amount of digits to compare. All right, what's the next? X of 0 minus x of 1, magnitude. Of course, it doesn't matter. You're writing like an x of 0 minus x of 1 or x of 1 minus x of 0, right? It doesn't matter because we are looking for the magnitude. And if you do this algebra, once again, it's very straightforward. And you can easily tell this is greater than epsilon. Then what we need to do is derive next step, x of 2, right? X of 2. Well, I'll leave you guys to find x of 2, 3, and 4. 3 more iteration steps on your own. Even 5 to 7 minutes. All right, go ahead. Well, yes, the correct answer, the root is 4. It's exactly 4. But how many iteration steps you reach there? How many? Or calculator told you so? 9. Good, good, very good. I had to go 8. Well, 8 steps probably. But 8 step, you are able to reach that solution. However, you have to go to step 9 to make sure that step 8 solution is the root.
I got
So you need basically 9 steps, right?
the error for x8, isn't it 0.00115, which is less than the error tolerance?
0.00115 is still greater than the accuracy epsilon.
That's why it's 9, right?
Exactly.
Okay.
Exactly right. This is very critical, okay? To get 4, yes, you need 8 steps. However, without step 9, you cannot tell that. Does it make sense? All right. All right. 9 makes sense. 9 makes more sense. Yeah, well, if you need to count, well, that means you're not given the superscript of number. Is that true, Kevin? I think you'd better to have that number there. You don't want to miss that number.
When I made it to X3 and it still wasn't in there, I just kept hitting enter on my calculator and switching the numbers around until I found it.
Oh.
So then I had to go back and count how many times I did it.
I see. I see it now. I see it now. That's the calculator. That's how you guys use the calculator. All right. Yep. But in the exam, you need to provide this information. Okay, which step you use, and the error.
So 4 is our steady state value.
Say that again. What is it? Yes,
4.
yes. It's a 4 is the final root. Right. I can gradually present the steps. So the x of 2. You substitute the x of 1 into g of x, and then you should end up with 2.5173. And then what you do is compare. And then the difference turned out to be 0.2951. Oh my gosh, we've seen what the difference is becoming bigger, right? Why is it becoming bigger? Don't freak out. It's just like this, right? Sometimes the slope is steep. Sometimes the slope is flat. It's not necessarily is going crazy. It's going not necessarily. Okay. You're approaching to the correct answer. Just don't worry. And then x of 3. And then do the same thing. You end up with this. Go ahead to check this. And then 3793. It's getting worse. Yes, that's true, but don't freak out. You're good. As long as you don't have any algebra calculation mistake. X4. Keep doing until x of 8.
Should it be x1 minus x to the power 2 when you're doing this, or did I do this wrong?
You mean here?
Yeah.
It doesn't matter, like I said, because you're looking for the magnitude.
Yep.
You flip this two, and then you get negative value, but still the
Got it.
okay. Yep. The this is the x. This is the x of 8. From x of 8, you got compare 8 with 7. 8 with 7. 8 and 7, you end up with this number. John got 0.00115, and basically saying, so you find it was still greater than the epsilon. So you have to go to x of 9, okay, because of this. X of 9, guess what? End up with same number. End up with same number with previous step. You're not immediately drawing the conclusion, okay? You have to have this written. As what? Okay, this is the moment you should say hooray. Is root. Okay, now you can tell the step 8, x value is the root.
Is there a certain number of decimal places you want us to go out? Because like my calculator went out 13 decimal places.
No.
But they weren't the same.
I mean,
So as long as we go out what epsilon is, then we should be fine.
Yes.
Okay.
Maybe one more will be more than enough to keep. Like John said, he obviously keep 5, right? He got 0.00115. That's nice. That's nice too. 13. Oh, no. Overkill.
End up getting, like, if these are polynomial equations, you could have multiple roots. So how do we know that when you evaluate it like this, you're not just running into another root that actually isn't? It's one.
Well, you are looking for a root by one particular initial value. Yes. How do you know you? Well, you are looking for the root. Yes, it's one of the roots. That's okay. I'm not looking for any particular root. I'm looking for one of the roots, and then you got it. And how to go to another route towards another root? I agree with you. That's about how to choose the different initial value. Right. Any other questions regarding this? This I don't think is very difficult, but just I think one thing you need to be careful is be paying enough attention on the difference between two methods. Remember, I mentioned two methods, Gauss-Seidel and the Newton. Right. Pay enough attention on the difference between two. And this is one thing you need to be careful. Don't do like it happened before. Okay, in the exam, I'm asking for Gauss, and some students give me the very detailed, very nice procedure and a very correct calculation for Newton. Well, guess what happened in the grade, right? So don't do this. And the second thing you need to be careful, I think, is just the algebra. When you use your calculator, make sure you're typing in the correct values. And also nicely present all of these steps. Nicely present all of these steps. So enabling me to tell whether you understand or not. Does it make sense? Because I have to grade you.
So the final answer is x to the 8, or is it 4?
Yes, it's x of 8 equals to 4. So
Both.
You know what I mean? This x of 8 equals to 4. You're saying x of 8 is the root, or 4 is the root. Well, my point is here. Okay, my point about the answer is here. You need, by here, you cannot stop, because from here it's still greater than accuracy. My point is, you have to go to step 9, and then you have to do this to tell, okay, eighth iteration is the root. Okay, and my point is here. This has point. Okay. As by point, it literally points, okay, in the exam. Okay, that's what I mean. It has point even. You stop by 8 here, well, you're losing this part of the solution. Well, you're losing point. Okay, that's my point. Because you're not justifying this 4 as the solution, as the root. You're not justifying. Any other concerns? Let me ask you a question. So check your answers. Tell me what if the given accuracy is as big as 0.002? Obviously, much bigger than the epsilon previously, right? Much bigger. So what is your solution? What is your root? So check what you have done and tell me what is your root. I give you guys some time, 2 to 3 minutes.
So I got the 7th iteration,
Which is equal to?
3.998.
Good, very good, very good. Yeah, very good. If that's the case, your 7th iteration equals to 3.9988. And then from there, you're checking 7 minus 6, right? And then what's the difference from there? What's the difference from there?
The error from 7 to 6 I got is 0.04215.
0.04. 0.04?
Oh, sorry, that would be the next one.
Absolutely not.
0.00115.
That's better. Okay. This guy, what do you see? It's already less than the new epsilon. I'll give you the new epsilon as a prime to differentiate from the previous one. Okay? So what's your conclusion here? X. Oh. 0, 0, 1. Is your 7 to 6 difference is a 0.00115? You sure?
No, my answer is x sub 7. That would be.
I know. So x to 7 to 6. 7 to 6
should be a 8 minus 7.
I know. This is this, right?
Yeah.
0.042 is the difference between 7 to 6.
Yeah.
So what you need to do is derive the x of 8, which is equals to what? 4.
9. Yeah.
Right? And then from here, what you're checking x of 8 to x of 7. The difference will be
0.00115.
0.0012. From here, you see what? less than epsilon prime. And what is the conclusion here? X of 7, which is equal to 3.9988 is root. Does it make sense? Everybody? This is obviously you can consider as the second example. Or second example. Okay. Once again, X of 7, you reach this value. By checking the difference with 6 step, you're seeing, okay, you need X of 8. From checking the difference between 8 and 7, you're seeing what? X of 7 is the root, because the difference between these two guys is already less than the required epsilon prime. That's why X of 7 is the root. Does it make sense, everybody? Because in the exam, the step number, you need to write them clearly. Okay, that's no matter how you calculate them, you need to write clear step number. Does everything make sense? And from this result, obviously, it's a very easy to tell. Tell what? With greater accuracy, what do you see? Lower resolution of the root. Does it make sense? Because you know the 4 is the exact root. Okay. These 3.9988 is close, but the resolution is not high enough. Does it make sense? You're sacrificing the resolution of the root to achieve what? What's the benefit? What's the trade-off? What's the benefit you're achieving?
Less iterations, quicker.
Exactly. Less number of steps of iteration. Makes perfect sense, right? So increased accuracy, you have less number of steps. However, the solution resolution is harmed. Okay, it's harmed. Not having enough resolution. No, not anymore. All right. And if this is okay, then let's talk about the next, which is here. This method could be we could talk a little bit about the undimensional case. Undimensional case. What does it look like? Well, first of all, you have as I said, n simultaneous equation, right? First equation, x1, x2, x up to x of n equals to c1, right? Or maybe c1, or well, just make it to be 0. Then second one, yeah, equals 0. Right? Up to how many? N, right? So how to derive the x? Well, this time you need to derive x1, x2 to xn. This time you have g1, x1, g2, x1 through xn. x2 equals g2 of x1, 2, all the way to n. xn equals to g sub n, x1, 2, all the way to xn, right? Does this make sense? And then when you do conducting the derivation, well, with initial values, initial value means what? x1 of 0, x2 of 0, all the way to xn of 0, right? These need to be given, or somehow you obtain in the first place. With these initial values, you derive what? x1 of 1, x2 of 1, right? All the way to xn of 1. x1 of 0, right? x2 of 0, up to xn of 0. Right? x2 of 1 equals what? g2 of x1 of 0, x2 of 0, and up to xn of 0. Right? It's the x2 of 1. And xn of 1 is gn x1 of 0, x2 of 0, up to xn of 0. Right? And after this iteration, what do we do? What do you do next? Checking, right? Checking. I'm checking specifically, where we checking? 1 of 1, x1 of 0. N-dimensional. It's not surprised that we need n epsilon accuracy. Of course, most of the time we probably want to make the accuracy same among different unknowns. It might be same, but make it more generic, more generalized case is labeling them differently. And then either hooray or x1 of 2, 2 of 2, up to xn of 2 for next step iteration, right? No, of course, it's going to be done by the first iteration step. That's of course impossible. Now it becomes n-dimensional. Wow, this jackpot is even hopeless, right? Even more hopeless, I would say. Yes, it doesn't make any sense. One-dimensional is super difficult, let alone n-dimensional. You need not only need luck, you need to cheat to win this jackpot. That's impossible. First step. No.
Would you ever set the errors to be different for each individual X1?
That's possible. That's possible. Why not?
And you're only done when all of the errors are within the tolerance.
I mean, if you're done one of them, you're done with one of them. You stop there. You stop X1. Then stop one. X1, you reach step 10. You got the less than epsilon 1. You're done with X1. The rest of the X2 through Xn, you keep using that X1 value. You're done. You're done. This is the solution. This is for n-dimensional. So extending the one-dimensional, one single equation to n-dimensional. So basically, you have idea how to handle this in the in any case. In any case. Now, let's talk about the second method. Not much time left, so we just started and leave the more details and examples to Wednesday. Second one, as we mentioned, called Newton Raphson method. This method is based on a little bit about it. It's based on what Taylor series. This method instructed in the 302 too. That's it.
And I'm taking 302 right now in conjunction.
Oh, probably not there yet. Probably not there yet. So maybe this is a new one. If it's a new one, we can slow down a little bit. Okay. But first of all, we need to understand what does it mean by Taylor series. Have you guys learned Taylor series before? For anything? Differential equation should do, right?
Yeah.
Have you?
Vaguely familiar from a calc class.
Say that again?
Vaguely familiar with it from a calculus class. I don't remember which one though.
Okay, good. So, a Taylor series is talking about what? Okay, it's talking about basically this. Okay. For example, if we just take the initial value as an example. If we give a, how to call it, perturbation. What does it mean by perturbation? Perturbation is something very small value, kind of interrupting the original x. How the resulted function value gonna change, or what's the result look like? The result looks like this. It equals to the original function value without any perturbation yet, plus the consequence. What is the consequence? Is this first order derivative of the function f, and then times the introduced perturbation plus times second order derivative with respect to x equals to s times d delta x of 0 squared, so on, so forth. Last term, you can write one more term to see the pattern easier. Okay. So what we really care is actually the most significant part of the equation. To simplify this result a lot. So what are you going to do is it is called neglecting the hot. By neglecting the hot, you only end up with what? Just the first two terms. Which means this part neglected because they're hot. This is the Taylor series. This is Taylor series that we are using. From which if you're assuming a function like this, function f of x equals to c, constant c. It doesn't have to be 0. Could be any constant c. Based on the Taylor series, it's equals to f. Oh, here, assuming this x plus 0 delta x 0 equals to c, and find x of 0 plus derivative x equals to x of 0 times delta x of 0 equals to c. And further, we are able to derive the delta x of 0 equals to constant minus f of x of 0 divided by derivative x equals to x of 0. We can stop here for here. What is hot? You mean here, right? What does it mean by hot? You guys understand in math? What does it mean by hot? Anyone knows?
Terms.
Good. High order terms. Higher order term. Or is it higher order term? Generally speaking, what higher order terms are? Look at these. Why they're called higher order terms? Square, cube, nth order. Higher order. Why higher order terms could be neglected? Why is that? Anyone knows?
Doesn't it have to do with like we want to work with stuff that's linear?
No. Oh, I think this needs to be.
Thing in the front that makes them smaller, makes them neglectable, like where you do the 1 divided by 2 factorial, 1 divided by 3, 1 divided by n factorial.
That's a very good point. However, that's not the major reason. Here, yes, is making them smaller and smaller. However, they're not the major reason. What's the major reason? Is here. This is way more significant. Why is that? You need to roughly understand this is a delta value. Delta value is what? Small. What does it mean by small? Way less than whom? What? Things less than 1, the value less than 1. If you give a square, cube, and even higher order, what happened? The value becomes what? Smaller and smaller. Does it make sense? It's not like the number greater than 1. You gave a 2. I gave you square and cube and nth order will become bigger and bigger, a lot bigger. However, it's less than 1, way less than 1. So square, cube, and nth order can only make that value a lot smaller, right? Does that make sense? That is the higher order. That's why they are negligible. Okay, that's why they're negligible. Okay, that's why they're hot. They're hot. We want to brush them off the back. So. All right, I think that's all for today. And thank you for attending today's lecture. And talk to you guys on Wednesday. I'm expecting to finish the grading either Wednesday or next Monday. Okay, I'm in the middle of it. All right, thank you. Bye now. Thank you.